All right, so today I want to talk about finding oxidation numbers. Oxidation numbers are just the green numbers on the tops that we've been using throughout this chapter, right? It's these things. How do these things come about? Because right now, what you've done, you've seen a chemical reaction, right? And then some wizard has come along and has been like, yo, magic! And then kabang, there are oxidation numbers. And I want you to learn that magic. How in the world do we actually get these numbers and get them right every single time? And to be clear, you will get it right every single time if you follow my rules. So first and foremost, I'm going to suggest you get a nice piece of paper. You can see I'm using this like big note card. And I'm going to say write these rules down. So if you need to pause me and go find a pen and a piece of paper, do it. But you want to write these rules down. And the reason you want to write these rules down is because you have open notes throughout this whole chapter, obviously. And so if you have them written down, it's going to be really easy to look over and say, hey, here are the rules. And I've written them down. And I can reference them as I'm doing them. So we're going to go through a series of 8 rules. And then at the end of this video, I have a couple of little quick experiments to show you. So let's start off with the first rule. And that is an element by itself has an oxidation number of 0. Now, elements come in lots of forms, and we'll talk about that in a second, but an element just by itself in the middle of a chemical reaction is equal to 0. So, let's say you come across a chemical reaction, and you see carbon. And carbon's all by itself, you know. It's something plus carbon yields something else. Well, then this carbon has an oxidation state of 0, period. So let's say you came across a really neat chemical reaction and it had Au, it had some gold in it. What would the oxidation state of gold be if it was all by itself? Great, it's also 0. And as a matter of fact, even iodine here. Now, iodine's a little tricky because it's got a subscript, right? But iodine only has one capital letter. It only has one element. So it's also 0. So things by themselves are 0. Pretty straightforward. Let's take a look at another rule. Okay, rule number 2 is this. All oxidation numbers in a neutral compound add up to 0. Neutral here means it doesn't have a charge, right? Oxidation numbers are the green things I've been writing on top. And so the sum, the total, the addition between them, all of it together becomes 0. Okay, so let's take a look at a couple more of these things as an example. Let's take a look here, for instance, at this compound, CH4, methane. Even though the numbers of C and H might be different, when I look at the whole total thing together, this whole group, it has to be 0. So what would the whole total group be for potassium nitrate here, KNO3? So to be clear, a lot of the times, the total is going to be 0. The elements by themselves are 0, and most compounds together are 0. And so 0 ends up being a really important number. And maybe you've noticed that so far as we're doing this. But 0 isn't always the sum. I said there's an exception. So let's take a look at one more rule, rule number 3. And rule number 3 says this, that a polyatomic ion, that is, an ion made up of more than one element, will have an oxidation total equal to the ion's charge. That's a lot of words in one mouthful. Let's take a look at it in practice, and I think it makes more sense. So for instance here, I've got the SO4 2-, the sulfate ion, right? And yes, S and O have different amounts. But together, this whole group doesn't add up to 0 because this thing right here is telling me they don't add up to 0. And so I'm just going to take this charge and copy it down. So the oxidation total of SO4, of the sulfate ion, is -2. So here in a second, edpuzzle is going to ask you a question, which is, what is the total on this chlorate ion? Right? What's the total oxidation number? What's the sum of all the parts of the ClO3-? These can be a little tricky. I get it. But together they're pretty straightforward And these three rules are going to be the kind of overarching rules of every single problem we do. So I've written them down here in kind of a neat way for you. All right, so I've been keeping track of the rules on this card so far. That an element by itself is 0, that oxidation number's sum in a neutral compound is 0, and that the oxidation number sum in a polyatomic ion is its charge. And I'll keep adding to this as we go along. But what I want to do is I want to show you having a card like this is really helpful. For instance, let's say we wanted to diagnose this reaction between sodium and iodine making sodium iodide. Okay, so we would need to figure out what would go in each of these three boxes. So let's look at the Na and the I2 here. They're both elements by themselves. So what has to go in this box? Now, NaI is a neutral compound, so what has to go in its box? Pretty good, right? Lots of zeros. Now, I want to be clear that Na and I may not be 0 each by themselves, but together they equal 0. And we need to deal with more of those rules here in a moment. Before we get to those rules, though, I think it might be cool to quickly see this reaction in person. I mean, this is a superreactive element, and this is a relatively reactive element. And I've never seen these two things react in person, so let's find a video of it really fast. This is from the Bunsen Burns YouTube channel, and you can see them adding quite a bit of iodine to some molten sodium. And the reaction's pretty energetic. It looks a lot like iodine reacting with other metals like magnesium or aluminum, maybe a little brighter in those sparks. Obviously that purple iodine vapor is quite dangerous to people. That's why it's being done in a fume cupboard, but might be something worth trying when we get back. I don't know, pretty neat. Alright, so let's come back and do some new rules. Rule 4 says that group 1A metals are always, and always means always in this case, +1. That is, if I have a metal from the first column in the periodic table, right, this piece here, it will always be +1. An alkali metal always is +1, period. And we can add another rule to that. That 2A metals are always +2. And this isn't news to you because these are the charges of the alkali earth metals as they are. You already know that this piece of the periodic table is +2, period. And so these two rules are kind of common sense almost. And actually, as a matter of fact, one more rule, and then I'll give you a little break to write them down, is that the halogens are going to be -1. At least in this class, there's an exception in real life, but let's ignore that. That means the halogens, the things that you've always thought of being -1, right? This column next to the noble gases, well, they're -1 in this case as well. So a set of these rules is really familiar to us. So let's give ourselves a moment to write those three rules down. Okay, let's call this 1A metals. And those are always equal to +1. Let's come up with another rule. Let's say the 2A metals, well, those are going to be +2. And one more thing to write down, which is the halogens, are going to be equal to -1. Always in this class. Those three things are true. Now, I guess it's important to note that these things are true only in one case, which is in compounds. If they're alone, the rules on top are more powerful. So now your notes probably look something like this, and that's great. And that lets us come back and actually do our first reaction. So I'm going to get these notes up here, and let's take a look at this thing we just watched the video of. Na plus I2 equals NaI. Now, right by itself, Na's here. It's all alone. So what's its number? We've also already said that iodine is 0 in the past. But now I have a compound, and it is true. This compound all adds up to 0. But I've got some new rules over here that I have to take into consideration. And sodium, what would sodium's oxidation number be in this case? Right? Because it says so right here, that 1A metals are always +1. Now, +1 has to equal 0, so I can't be 0. So what's I have to be? And you know that because iodine is a halogen, or if you want to think about it, I have to cancel +1 with something to equal 0. I don't care which way you get there, you're going to get there. Now that's a pretty neat trick already. We just made the oxidation numbers for sodium iodine to make sodium iodide. And now I can do something else. I could draw a line connecting sodium to sodium and ask you, hey, what happened to sodium? Was it oxidized or reduced? So what do you think I'm going to do right now? Was sodium oxidized or reduced? And now we're getting to a spot where we can look at a chemical reaction and figure out what's happening in it by a set of rules. Let's do another one together. This is another reaction I've personally not seen. But that's for good reason. Chlorine gas is mustard gas, or at least part of it, and I really don't want to deal with that if I don't have to. Right off the bat, there are two things in this reaction which I can ignore. Right? Two things which are 0. Now, this thing together is 0 because there's no charge over here, right? Together, this whole thing is 0. Ooh. But that's not the end of the story because each element within this compound has its own charge. Now, calcium is a 2A metal, so what's its oxidation number have to be? And chlorine is a halogen. Now that means it's a -1, and this is where students tend to get confused. Because look, Mr. Nedick, +2, -1, those things don't add up to 0, and you're absolutely right. +2 minus 1 does not equal 0. However, it's important to notice this is for each atom in the molecule, right? CaCl2. And so what I have here is a situation like this. Let me grab a piece of paper and draw it for you. So I've got a situation like this, right, where I know the calcium has to be at a +2. And to have CaCl2, I've got to have like 2 chlorines, right? 2 of these things bound to that one calcium. And I know that halogens are a -1, so each one of these things is at a -1, and together they are both attacking this +2, or more accurately, both taking one of calcium's electrons, to cancel it out so that the total of all of these things together is 0. But we don't write it that way. We write it what each atom's doing. So yes, these things don't add up to 0 how I've written it, but they do add up to 0 for the molecule. I know that's a little tricky, but again, what we want to do is talk about the individual atoms, not the overall piece, if that makes sense. So this would be the correct answer here. You'll get lots of practice with this on your homework tomorrow, I promise. And it will make more sense as you do it. This leads me into my favorite rule, rule number 7, that oxygen in a compound is -2, except in a weird thing called a peroxide where it's a -1. Now, right off the bat, Mr. Doyle, Mr. Sullivan, and I have talked together, and whenever we have a peroxide, I will tell you exactly in the problem, hey, look out, this is a peroxide. So this is a special case you should have memorized, but oxygen being -2 is your friend in this. If you know that, it's going to be a lot easier to diagnose a reaction. Well, let's keep that in mind here and look at a quick example. The burning of magnesium in the presence of oxygen. So this is not a peroxide, so I'm going to cover that up. So, in this reaction, oxygen has to be a -2. So what's magnesium? Right? Because these things together have to equal 0. And there's only one of these to cancel one of these. If this is -2, it has to be +2. Let's do another one. This is not a peroxide. It's normal. It's the burning of hydrogen to make water. So, if I tell you this is +1, then what's oxygen have to be? And to be clear here, it has to be -2 because oxygen in a compound is always -2. Or you could think about it, I have 2 different things that are +1. So I have +1 +1 equaling -2. So together this whole thing is still 0, even though it's +1 -2. All right, let's do another one. Uh-oh, I've got a peroxide. So this one's different. I know that in peroxides, this must be a -1. But if this is minus 1 times 2, this whole group here is like a minus 2, right? Which means this whole group here has to be a plus 2. Which means each of these has to be a plus 1. But that makes sense because hydrogen's often plus 1. You see how oxygen's going to make your life easier? If you know oxygen, you can kind of work backwards from it. So let's add a rule to our notes really fast. And that rule is that oxygen is going to be a minus 2 in compounds and a minus 1 in peroxides. Now, I've given you a little foreshadowing. Apparently the last rule has to be about hydrogen, so we'll get there in a second. But we're getting really close to being able to actually make our own predictions about any chemical reaction that's oxidation reduction. So let's take a look at one more. Let's make some rules for hydrogen really quickly. And the rules are pretty straightforward. Hydrogen is a plus 1 with nonmetal and a minus 1 with a metal. Now these are pretty rare. They're called hydrides, and they're important, especially in like energy storage. Long term, this is an area of research, but most of the time, hydrogen is going to be a plus 1. So here's hydrogen, and oxygen's a nonmetal. So what does hydrogen have to be? And here's ammonia. Ammonia is bound to nonmetals, so what's hydrogen got to be in this case? Let's actually stick with this for just a second. I have something where it's like NHHH, right? And if each one of these is a plus 1, right, then what does the center charge on this nitrogen have to be? Because this whole thing adds up to 0. And so if I have 3 plus 1s, I have to have a minus 3 on the end. Okay, we're getting there. Let's take a look at a hydride, right? A metal-bound one. We know that sodium is a 1A metal, right? And by our rules, 1A metals are always plus 1, always. So this has to be what? What does sodium have to be? And if that's plus 1, it has to be a minus 1 on hydrogen. And that makes sense by this rule here because this is a metal and this is a hydrogen. And when hydrogen is bound to a metal, it's a minus 1. Well, here's why. You can see it in real life. So with that, let's update our rules and get them to their final state. And here we go. If you have these rules written down and have them to your side whenever you're using it, you won't miss any questions on this stuff. Now, it takes a while to get familiar with them and kind of move around, but most students find this pretty directly straightforward. Not everyone. If you get stuck, make sure you kind of work through the problems with yourself, and if you can't get it from that, then shoot your teacher an email and we'll help you. But with that in mind, I think it'd be a good idea to take a look at this in real life and show you how I do things. So these are our rules. And this is the basic process that I like to use. I like to check in the problem if there's oxygen, and then if there's a halogen, and then just kind of work my way through the rules. Right, I like to start, if you will, here, and work my way up. And it doesn't really matter what you do, although oxygen is generally your friend, right? Oxygen generally will make life easiest for you. So let's diagnose a problem, a real difficult reaction, and then let's look at it in real life and appreciate what's going on, because it's the first time you'll be able to look at a redox reaction and actually say, hey, I get what's going on in this case. So we're going to be reacting potassium permanganate, and really the permanganate ion, and we're going to make it into the manganate ion. And this is the first part of this reaction. Now, I know that all the oxidation numbers in a polyatomic ion add up to the charge. So what do all of the numbers in MnO4 have to equal in this reaction? All right, so all of the numbers have to be minus 1 because this number here tells me minus 1. Now, if I look at this, I don't have any rules for Mn here, but I do have a rule for oxygen, which is that oxygen is a minus 2 in compounds, unless it's a peroxide, and this isn't a peroxide because I didn't tell you it's a peroxide. So what does each atom of this O4 have to be? Which each atom here, what's its oxidation number? So it's a -2, right? And I've got 4 of them. So each atom's a -2. So this whole group here, right, this whole area, it must be -8. Now, normally we wouldn't write this down. It's unnecessary. It's extra information, right? The oxidation state of oxygen is -2, period. But the question I'm asking my brain right now is what for manganese combines with -8 to equal -1? Or algebraically, what -8 equals -1, right? That's the problem. Well, the only thing that makes this statement true is if manganese is a +7. So for these things that aren't on the rules, you want to solve all the things that are on the rules and then fill in the blanks. And this one is particularly hard. So if you're looking at it and being like, oh, I don't understand it, take a breath, you'll be okay. Let's look at one that's really similar here. Okay, so first and foremost, what's this whole group got to be? This whole manganate ion, what does it need to be? The whole thing together. And it has to be -2 because the rule here says that all the oxidation numbers in a polyatomic atom add up to its charge. Okay, well, let's do the same thing. Oxygen is still in a compound. Oxygen is still -2, which means this whole group here is now -8 still. But something's changed between these two, right? So manganese no longer is +7. What does it have to be now? But this tells us something, right? Because the number went down, which tells us manganese was reduced, which I could have actually seen here because the electron was a reactant. And when electrons are reactants, it's a reduction half reaction. So this is going to happen. But I have a trick up my sleeve. You see, this isn't the only reaction that happens because once I have the manganate ion, well, guess what? It's going to react with the water to keep the reaction going forward. Now, I don't care about the electrons or even really the water here. I really just care about this MnO4 2- and this MnO2 for the moment. So I already know this. We just did this one. This is +6 -2. Now, MnO2, it's a compound by itself. It's not a polyatomic ion. So what's this whole group got to add up to? Right? Because all neutral compounds add up to 0. And this isn't a peroxide. It's a normal compound. So oxygen has to be what in this reaction? Now that means each oxygen is -2, right? So if I have 2 -2s together, Mn can't be +2. It has to be what? Because again, this manganese has to be responsible for canceling both oxygens. Now again, there is stuff going on out here, and I don't really need to look at that too much for the moment. So let's take a look at this kind of in the big picture now. Again, I'm not really caring about this stuff here because it's not going to help you understand what I'm about to show you in a demonstration. But I want you to see that this permanganate is going to get reduced to the manganate ion, and then the manganate ion is going to get reduced again to the manganese dioxide here. So what's going to happen is this reaction is going to go in steps where one thing happens, then a new product forms, and when that new product forms, it's going to react again. So we should see this reaction kind of go forward slowly. So I'm going to take you to the lab at Rockhurst where I filmed this a couple weeks ago and actually show you this reaction happening because it's a really pretty one. But in the back of your mind, I want you to be thinking, hey, I made a prediction. This thing is going to react once and then react again. So let's cut over to Rockhurst here really fast. You'll notice I have a 500 milliliter Erlenmeyer flask, and I filled it up with water. I'm going to add a stir bar to it and go ahead and turn on the stirring and add an arbitrary amount of sodium hydroxide. I'm going to go ahead and speed up the stirring here for you so you don't have to watch it dissolve. And just about done there. I'm going to add potassium permanganate, which is KMnO4. It's in the +7 state. So this is our starting material. You can see I'm not adding a lot of it at all, just the tip of a scapula. Kind of cool to see it stir in there with the vortex. Now to this, I'm going to add normal table sugar. This is a great reducing agent, and it's going to be our source of electrons. So here's the sugar. And that reaction is pretty obvious. So this is our first reduction here. Okay, speed it up for you just a moment here. It looks pretty stable, so I'm about to add more sugar to push the reduction forward further, to make that second reaction happen. And there it goes. And you can see the second reaction pretty obvious from a color change. Now, manganese dioxide is black, but it's very, very small particles, so the color change here is coming from the particles getting bigger, but the reaction's not changing anymore. So that's it. That's this reaction, and hopefully you can see it from our predictions to this reality. Now, I think this reaction's most interesting when it's played back end to end. So really cool to see that color change there. Anyway, that's all for today. You have no homework tonight, and I'll see you tomorrow. Buen camino.